Here's an assumption almost everyone makes about the internet, without realizing they're making it. You send data in a specific order. The network carries them to the destination. The order you sent them is the order they arrive. It seems almost too obvious to state. Of course they arrive in order. You sent them in order. Except the internet doesn't work that way. Not at all. The packets you send don't travel together. They don't stay in sequence. They don't even necessarily take the same route. Each one is an independent piece of data, released into a network that treats it individually. And individually, packets can take completely different paths, encounter completely different delays, and arrive in a completely different order than they were sent. Out-of-order delivery is not a bug or a rare edge case. It's a normal consequence of how the internet moves data, and what different systems do about it is one of the more revealing distinctions between different networking approaches. To understand why packets arrive out of order, you have to understand one thing clearly. The internet is not a pipe. A pipe is a single, fixed channel. What goes in one end comes out the other in the same order, by physical necessity. If the internet were a pipe, ordering would be guaranteed. First in, first out. But the internet is not a pipe. It's a network, a web of interconnected paths where data can travel from source to destination through any of multiple possible routes. At each rotor along the way, a forwarding decision is made, given where this packet needs to go, which outgoing link should it use. Different packets from the same connection might get different answers to that question, and different answers mean different paths, different amounts of congestion along the way. Imagine sending packets 1, 2, and 3 in rapid succession. Packet 1 takes a direct route, 3 hops, low congestion, arrives in 40 milliseconds. Packet 2 takes the same route but hits a congested router on the second hop, queues briefly, arrives in 65 milliseconds. Packet 3 gets routed differently. A network change caused the router to prefer a different path, takes 5 hops instead of 3, but encounters no congestion, arrives in 55 milliseconds. Order of arrival, 1, 3, 2. Not the order they were sent. Nothing went wrong. The out-of-order arrival is simply a consequence of the independent, dynamic, distributed nature of packet routing. This happens more than you might expect, for several specific reasons. Load balancing is one of the most common. Many routers and network devices deliberately split traffic across multiple parallel paths to distribute load, a technique called equal-cost multipath routing. Different packets from the same connection get sent down different links simultaneously. If those links have even slightly different latencies, different lengths of fiber, different numbers of intermediate hops, packets traveling the slower path arrive after packets that left later but traveled the faster path. Retransmission creates out-of-order arrival at a different level. In TCP, when a packet is lost and retransmitted, the retransmitted copy arrives after the packets that were sent after it, because those later packets took their original path while the retransmission had to be triggered by a timeout and sent again from scratch. The later packets arrive first. The retransmission arrives after them, filling a gap in sequence that shouldn't be in the middle. Network path changes during a connection can also produce reordering. If routing tables update while a connection is active due to a link failure, a convergence event, or a deliberate traffic engineering change, packets that were in flight on the old path arrive around the same time as packets already traveling the new path. Two streams merging, potentially interleaving, potentially out of order. So the network delivers packets out of order. The question is, what do you do about it? The answer depends entirely on what the data is and what the application needs. For applications that need ordered, complete data, web pages, file transfers, database queries, the answer is TCP, and the answer is to fix it transparently before the application ever sees it. TCP uses sequence numbers, a counter attached to every byte sent, to enable the receiver to detect and correct out-of-order arrival. When packets arrive out of sequence, the receiver doesn't pass them to the application immediately. It holds them in a buffer, ordered by sequence number, waiting for the gaps to be filled. When the missing earlier packet arrives, whether it was just delayed or had to be retransmitted, the receiver fills the gap, completes the sequence, and delivers the data to the application in the correct order. From the application's perspective, nothing unusual happened. Data arrived in order. The reordering, the buffering, the waiting, all invisible. TCP absorbed the chaos of the network and presented a clean, ordered stream to the application above it. This transparency is one of TCP's most valuable properties. Applications built on TCP don't need to think about packet ordering. They don't need to implement reordering logic. They write to and read from what looks like a continuous, ordered byte stream, and TCP guarantees that it stays that way regardless of what the network actually did. But TCP's reordering fix has a cost, and it's the same cost we've seen in other contexts: time. When a packet arrives out of order, TCP has to wait for the missing earlier packets before it can deliver anything to the application. If the missing packet was merely delayed, the wait is brief. If it was lost and needs to be retransmitted, the wait includes the retransmission round trip. This head-of-line blocking is one of TCP's significant performance limitations, particularly for applications that don't strictly need ordered delivery, but are using TCP because it's the default reliable transport. For real-time applications, voice, video, gaming, UDP is used precisely to avoid this. UDP delivers packets as they arrive, in whatever order they arrive, without buffering or reordering. A packet that arrives out of order is immediately passed to the application. If the application cares about order, it has to handle it itself. If it doesn't, if an out-of-order video frame is simply displayed in the position it arrived, or if a missing game state update is interpolated from surrounding data, then skipping the reordering machinery produces lower latency and continuous flow. A video call receiving frames in the order 1, 3, 2 might simply display frame 3 after frame 1 and discard frame 2 when it arrives late. The visual result is a brief glitch, imperceptible at 30 frames per second. Far better than holding frames 3 and all subsequent frames in a buffer while waiting for frame 2, producing a freeze. Out-of-order delivery becomes genuinely dangerous when it happens at the application level, not in the network layer, not handled by TCP, but in the logic of what the data means. Consider an application that processes events, user actions, state changes, transactions. The events are sent in a specific order, because the order matters. Event A must be processed before event B, because B depends on the state that A establishes. If B is processed first, the result is wrong. If this application uses TCP, the events arrive in order. No problem. But many modern systems, message queues, distributed databases, event streaming platforms, process data through multiple parallel workers, across multiple servers, over multiple network connections. At some point, the ordering guarantee of any individual TCP connection isn't enough, because the events are moving through a system with multiple paths, multiple buffers, and multiple processing stages. A message queue might deliver messages to a consumer in the order they were published. But if the consumer processes them in parallel across multiple threads or machines, the processing order can diverge from the delivery order. Event A is delivered first but takes longer to process. Event B is delivered second and processes immediately. B finishes first. The application state reflects B before A, which was never intended. This is out-of-order delivery at the application level, and it's a pervasive challenge in distributed systems design. Solutions include sequence numbers at the application level, explicit ordering guarantees in message queue configurations, event sourcing architectures that store events in order and rebuild state by replaying them, and distributed consensus protocols that ensure all nodes agree on the order of operations before committing them. The common thread through all of these, TCP's sequence numbers, UDP's application-level ordering, distributed systems event sequencing, is that ordering is never automatically guaranteed by the network. The network delivers packets independently on their own schedules via their own routes. Any ordering guarantee that exists is something built on top of that delivery, a mechanism added deliberately at some layer to impose sequence on a system that doesn't inherently maintain it. Knowing this changes how you read data. When a system delivers things in the right order, someone designed it that way. They chose a transport that provides ordering guarantees, or they built ordering logic themselves, or they structured their data so that order doesn't matter. When things arrive out of sequence, the cause is almost always that some layer in the stack made a choice, implicitly or explicitly, to not enforce ordering. The internet moves packets. it doesn't promise to move them in sequence. Every ordered byte stream you've ever received was put in order by software running at the endpoints, quietly, invisibly, so seamlessly that it's easy to forget the chaos it's constantly correcting underneath.